I am Dr. Narayanasamy, retired professor from Department of Production Engineering, National Institute of Technology, Tiruchirappalli, Tamil Nadu, India. Today I am going to talk about superplasticity and superplastic deformation. What is superplastic deformation? What do you understand from this? When you say superplastic deformation, you will get very large deformation. Very large deformation is possible. Larger strain is possible. Very high elongation is possible. Very high elongation means several hundreds to few thousands, in the order of several hundreds to few thousand. You cannot imagine the deformation at all. Lead, for example, take lead and tin electric alloy, which exhibited more than 3200 percentage elongation. It is exhibited in the London Museum. For superplastic deformation, there are certain conditions we have to meet. One is grain size. Grain size should be ultra fine. Ultra fine grain should be less than 10 mm, less than 10 mm micrometer. Temperature of the deformation should be greater than 0.5 times of T melting point. Then we talk about deformation. What is elastic deformation? What is elastoplastic deformation? What is plastic deformation? In the case of elastic deformation, stress strain curve will be linear. In the case of plastic deformation, stress strain curve will be non-linear. In the elastic deformation, the original shape will be retained once the load is released. In the case of plastic deformation, there is a permanent change in the shape. Mechanism of plastic deformation. Deformation. The conventional metal, slip and tuning will take place. In the case of superplastic deformation, grain boundary sliding will take place. What is slip? We'll see what is slip. Slip is nothing but movement of one atomic plane with respect to another atomic plane. What is twinning? In the case of twinning, you will get mirror image after deformation. In the case of superplastic deformation, grain boundary sliding will take place. Grains will not be disturbed. Take for example, a gunny bag of moong dal. If you give you a punch on the gunny bag, you will get an impression on the gunny bag. What will happen to the moong dal? The moong dal grains will be reshaped by sliding. The dal grains are not broken. It is rearranged. By rearranging the grains, the impression or deformation will be taking place. This is grain boundary sliding. This is what happens to superplastic deformation. This is the mechanism of superplastic deformation. Then we'll talk about deformation. Only ductile metals are suitable for plastic deformation. The conventional stress strain curve, we see this is plotted between engineering stress and engineering strain. Engineering stress versus engineering strain. This curve is linear up to the elastic limit. Then yield stress will be taking place. Yield stress is nothing but onset of plastic deformation or the beginning of plastic deformation. Then the engineering stress increases with increasing amount of strain. Maximum load is reached. Maximum load or maximum stress, ultimate tensile stress is reached. Then the stress decreases with increasing strain. At the maximum load point, at the ultimate tensile stress point, the necking begins. Necking starts. Necking begins. Here, the nucleation of voids will be taking place. The nucleated voids will grow in size. Ultimately, one void growth will take place. One void will join with another void. That is called void coalescence. The load carrying ability is lost. Then fracture will take place. Up to the maximum load or the ultimate tensile stress, The plastic deformation is uniform. Uniform deformation. When you say uniform plastic deformation, volume constancy principle can be applied. When you say volume constancy principle, there is volume before deformation is equal to volume after deformation. In the case of beyond ultimate tensile stress point up to fracture stress, it is non-uniform deformation. Here, volume constancy principle cannot be used because volume is not constant here. Here mass constancy principle can be used. Mass before deformation is equal to mass after deformation. Here elastic strain is negligible because elastic strain is very small amount. After the maximum load, the deformation is non-uniform. Up to the maximum load, volume constancy principle can be applied. Beyond the maximum load, volume constancy principle cannot be applied. Volume before, in the case of volume constancy principle, volume before deformation is equal to volume after deformation. When the maximum load is reached, voids are nucleated, void grows in size, bigger voids are developed, one void may join with another void, which is called coalescence, then load carrying ability is lost, finally fracture will take place. Hence, in the non-uniform deformation case, mass constancy principle can be applied. Mass before deformation is equal to mass after deformation. The best example for non-uniform deformation is powder metallurgy parts, powder metallurgy forging and extrusion deformation. Here, mass constancy principle can be applied. Up to the maximum load, volume constancy principle can be applied. For example, in the case of metal forming, up to maximum load only it should be considered. Volume constancy principle can be applied. Beyond the maximum load, mass constancy principle can be applied. So here, best example is powder metallurgy parts. True stress, true strains are important large deformation in ductile metals. Sigma represents the actual stress taken by the material. Sigma is given to load by instantaneous area of cross section. This is true stress, stress taken by the material, actual stress taken by the material. Sigma is nothing but true stress. S is nothing but engineering stress. Engineering stress is given by load divided by initial area of cross section, which is a constant. So S not representing the actual stress taken by the material. The relationship between sigma and S is as follows. Sigma equal to S into 1 plus E. D epsilon equal to, we can derive that true strain can be derived from this expression. D epsilon equal to dl by L. So here ln of 1 plus E equal to E minus E square by 2 factorial plus E cube by 3 factorial minus E4 for 4 by 4 factorial. When the amount of strain is small, higher order terms can be neglected. Therefore, in the case of elastic deformation, both sigma and S are same, and epsilon and E are also same. When the epsilon true strain is has additive property, whereas E engineering strain has no additive property. For example, consider one direction strain only. Here in the case of true strain, total strain is summation of epsilon 1, epsilon 2, epsilon 3, etc. Whereas in the case of engineering strain, it cannot be added. Take three-dimensional size. Three directions are perpendicular to each other. Three perpendicular axes are x, y, z directions, or 1, 2, 3 direction. Take rectangular plate. It has length, width, and thickness. Assume that the plate is subjected to tensile load. Here, volume is constant till the instability point. When you apply volume constancy principle, the summation of three different strains, in the three different mutually perpendicular directions. That is epsilon 1 plus epsilon 2, epsilon 3 equal to 0. This is strain in the one direction, this is strain in the another direction, strain in the third direction. Summation of epsilon 1, epsilon 2, epsilon 3 is equal to 0. Summation of three strain is mutually perpendicular to each other, strains are equal to 0. In superplastic deformation, instability point is postponed. Larger deformation is possible. Larger elongation is possible. So, because of superplasticity, the deformation produces essentially neck-free elongation. The neck-free elongation is many hundreds of percentage or few thousand in the metallic materials in tension. It is a deformation process which produces neck-free elongation in tension. For superplasticity, materials should have ultra-fine grain size. The grain size should be less than 10 micron, less than 10 micron. Temperature of the deformation should be greater than or equal to 0.5 times of T melting, Tm, where Tm represents absolute melting point. The constitutive relationship sigma is given by sigma equal to k into epsilon dot power m, where epsilon dot is the strain rate, m is the strain rate sensitivity, k is a constant, sigma is a true stress. M determines the stability of the flow. In the case of tensile stress, true strain is given by nominal strain plus 1 plus E, 1 plus E. In the case of true strain can be determined using this expression. True strain is given by 1 ln of 1 plus E, where T is represented true, N represents the nominal or engineering strain. We'll talk further about constitutive relationship. Sigma true stress is given by K dash, it's a constant, into epsilon power n. N is the Stern-Gardner exponent, into epsilon dot power m. Epsilon dot is strain rate sensitivity, strain rate. M is the strain rate sensitivity. M represents the strain rate sensitivity. For temperature below 0.4 times of melting point, M is close to 0. N lies between 0.1 to 0.3. So sigma T is given by K into epsilon power n. For superplastic deformation, N is 0 and M varies from 0.3 to 0.5. 0.3 to 0.9. For Newtonian flow, viscous material, N is 0, M equal to 2. Previously, as I said earlier, sigma is given by sigma equal to K into epsilon power m, epsilon dot power m, where epsilon dot is the strain rate. For temperature, here for Newtonian viscous material, N is 0, M equal to 1. For temperature and grain size dependence, sigma is given by K